Welcome to The Explainer. You know how your phone can just instantly find every single picture of your dog? Ever wondered how that actually works? Well, today we're going way beyond that. We're going to dive deep into the mechanics of how an algorithm can look at a super busy photo and nail every single object inside it.
Just look at this. A computer didn't just see dog or bike. No, it drew these super precise boxes around them and even gave itself a confidence score. So how does a machine go from a bunch of pixels to this level of, well, understanding? That's the big mystery we're going to solve together today.
So, here's our game plan. We'll start with the big question of how computers see it all. Then, we'll meet a lightning-fast algorithm called YOLO. We're going to peek inside his digital brain, learn to speak its language, and then, for fun, we'll flip the script and see how machines can build images up from scratch.
All right, let's jump right in. You know, the biggest challenge is teaching a machine to see the world like we do. For us, a photo is a memory, a story. But for a computer, it's just a giant spreadsheet of numbers for colors. So how on earth do you bridge that gap?
Well, this whole task, finding and naming objects in a picture, has a name. It's called object detection. Now, there are a bunch of ways to tackle this, but we're going to focus on one of the absolute cleverest and most game-changing methods ever created.
And that brings us to the star of today's show, an algorithm with a pretty great name, YOLO. Yep, it stands for You Only Look Once, and believe me, it completely revolutionized real-time object detection.
The name really tells you everything you need to know. See, older models had to scan an image over and over again, kind of like looking through a magnifying glass. But YOLO, it takes one single glance. It processes the entire picture all at once to figure out what's what, which makes it unbelievably fast and efficient.
And you don't have to take my word for it. This right here is the proof. The specific version we're looking at, YOLO v2-Tiny, which runs on a lightweight framework called Darknet, needs almost 5 times less processing power than a comparable model. That's not just a little better, that's a massive leap in performance.
So you're probably wondering, what does this digital brain actually look like on the inside? How is it built to be so darn fast and effective? All right, let's pop the hood and take a look. Okay, I know, this looks like a lot, but just follow the data with me. The image comes in at the top and then flows down through all these layers. Think of each one as a filter, pulling out more and more complex features. First simple edges, then shapes, then textures. But the real magic, the secret sauce, is at that very last layer, predict_conv. See that weird string of numbers in the output column? That's the code we need to crack.
These numbers, 13 by 13 by 425, they're not just random. The best way to think about it is like a 3D cube of data. It's a super condensed summary of everything the model has learned about the picture. It's the key that unlocks all those detections.
And that's the big question, right? This is the puzzle. If we can understand what this three-dimensional block of numbers is telling us, we can translate the network's raw brain power into those perfect little boxes on our image. So let's break it down.
Okay, let's do it. Let's pull this thing apart, piece by piece. We're about to translate 13 by 13 by 425 from machine speak into plain English. So that output, it's basically a highly organized report. The 13 by 13 part gives us a map grid, and the 425 tells us how much information is packed into every single point on that map. Now, where does 425 come from? Well, it's just 5 times 85. So let's figure out what those two numbers actually mean. First up, the 13 by 13. What the model does is it mentally lays a 13 by 13 grid right over the image. Each one of these 169 cells becomes its own little detective. This just simplifies the problem, right? Instead of searching the entire image for a dog, each cell's only responsible for yelling, "Hey, I found something," if the center of an object lands inside its little square. Okay, now for the number 5. For every single one of those grid cells, the model doesn't just guess one box. It actually proposes 5 different potential boxes. And these aren't random guesses. They're based on common object shapes the model has seen before, called anchors. This gives it a huge head start for spotting things of different shapes, like tall, skinny people or long, wide cars. And that brings us to the last number, 85. This is the real meat of it. For each of those 5 boxes, the network spits out 85 data points. You get 4 numbers for the box's position and size, 1 number for its confidence, like how sure it is there's anything in that box, and then you get 80 numbers that are probability scores for 80 different things, like dog, bicycle, or person. It's a full report card for every single guess.
But as you can imagine, this process creates a huge mess.
hundreds, maybe thousands of potential boxes all over the place. So a really important cleanup phase has to happen. First, the raw numbers are converted into real coordinates. Then they're scaled up to fit the original image. Finally, this super clever process called non-maximum suppression kicks in. It looks at all the boxes piled on top of each other, throws out the ones with low confidence, and picks just one winner. That's how we get those nice, clean detections in the end.
So we've just seen how a network can break down an image to understand what's inside. Pretty cool, right? But what about doing the exact opposite? Let's take a look at how a computer can take a tiny bit of information and build a bigger, more detailed image from it. This is the art of upsampling.
The magic behind this trick is something called a transpose convolution. So a normal convolution shrinks an image down to find features. A transpose convolution does the reverse. It takes a small input and expands it, learning how to intelligently fill in the blanks. This is absolutely fundamental for any AI that generates images like DALL-E or Midjourney.
And here's a perfect example of its power. On the left, you've got this tiny pixelated image of a dog. On the right is what you get after just one transpose convolution layer. Now look closely. It didn't just make it bigger, it intelligently smoothed out the pixels and kind of guessed what the missing details should be to create a much cleaner, higher resolution version. So let's wrap this all up. What are the big takeaways? First, we saw how YOLO tackles object detection. It divides an image into a grid and makes a ton of predictions. The real secret sauce is knowing how to decode that final block of data, that output tensor, which holds all the secrets. And on the flip side, we learned that transpose convolution lets machines do the opposite, not just to see, but to create by building bigger and better images.
Which leaves us with one last thought. We've built these incredibly powerful tools that can see and even create our visual world with shocking speed and accuracy. The technical challenges are being solved one by one. So the real question that's left for us is, what do we want to point this powerful new eyesight towards?